Hi to everyone. So the work that I'm going to present today is part of a bigger effort that we are undertaking in Cambridge, in which we are looking at the impact of this new hardware technology that are coming up in the data center space. And we are trying to understand the impact that they have on top of the existing software stack. So let me just plug this in. Okay, so if we look at data centers in the last 10 years, we've seen that we started basically like 10 years ago when big companies like Microsoft, Google, Amazon, and so on started sort of moving away from traditional HPC cluster and actually looking at commodity off-the-shelf servers because they figured out that it was more cost-effective in order to handle their workload. Then people have been looking how you can further optimize performance by effectively customize the server layout. So we can remove a unused component and, for instance, make more space for more storage disk or more memory banks. Then some people also have been looking at the network interconnecting the servers. And there have been several proposals. One that I want to call out here is SeaMicro. So SeaMicro is a company that has been now bought by AMD. And basically, they're selling this appliance that is a 10-rack unit, so something about this size, where actually you can have 500 cores interconnected using 3D Torus topology. So as John was saying, similar to what people were doing in the HPC world. And you can have very high density, very high bandwidth, and low power consumption. And more recently, there has been another interesting design point that has been explored by this company that was called Calzida. Unfortunately, they closed their business operation beginning of the year. But basically, their model was that you can have on the same, they use a system-on-a-chip design in which you can have on the same die the CPU cores, they were using ARM technology, the memory and I/O controllers, and then you can have also the distributed switch. So they're all integrated on the same die. So you can have very, very low latency between the CPU and the switch, or the NIC, if you will. And finally, and this is actually today's story, Intel is proposing what they call Rockscale Architecture, where the main feature is that you have silicon photonics. So you can have very, very high bandwidth. So currently it's in the order of 100 gigabit, but they claim you can reach up to a terabit in the near future. And effectively now you can have a design in which effectively the distinction between local and remote resources becomes sort of like fuzzy, because now the bandwidth that you get between your server and across servers is getting very similar. So if we now step back and we look what happened from a sort of like deployment perspective, we see that 10 years ago, effectively the sort of unit of deployment was one rack unit, the server. And then increasingly, we start thinking in terms of 2 rack unit, 4 to 10 rack unit, and now we're actually at the rack scale. So what we are arguing here is that now before there was a bit of, actually more than a bit, like a lot of difference between the intra-server bandwidth and the inter-server bandwidth. But nowadays, we are actually getting closer. So what we are arguing is that we should now start thinking in terms of rack-scale computer. So see the rack as now the unit of computing or unit of deployment inside the data center. And so what we are observing that there is a sort of shift between thinking of a server as our sort of optimization target and thinking of the rack instead. So we think it's a good time for us as a system programmer, system designer, to actually rethink some of the assumptions and see how actually we can take advantage of this new technology. Now, of course, this is going to be a very long process because the entire software stack is very complex. So here we just started from a very first step, that is looking at the network stack. And the first question that we want to answer is, okay, so are we just talking about a faster network? So silicon photonics or some of the other technologies that we just discussed are just going to provide us with, instead of having 1 or 10 gig, now we have 40 gig, 100 gig, and so on, or they are fundamentally different. So there are some features that we can really exploit in our design. So it's really hard to answer this question in a final way because clearly it's a moving target. People are still debating which are the best design points. However, we can speculate that at least there are 2 sort of emerging trends that we are seeing. So the first one is that since we are having a lot of bandwidth that is now available to a single server, it's going to be very tricky to have a traditional single switch that has enough backplane capacity to operate at full bisection bandwidth. So the sort of design that is emerging is what is called a distributed switching fabric. That is the idea that now every server is also operating as a switch on behalf of other nodes. So just to give you an example, this is a topology that is used in the SeaMicro box and I was mentioning before, or the HP Moonshot, that is another similar platform, where the idea is that if you want to move from one node to another, effectively you have to go through multiple hops. So if I want to go from here to here, I actually have to go hop to reach the other nodes. And immediately you can see that compared to traditional network, now we have a much higher path diversity because between a source and destination, now the number of paths that we have explode. Second is that now we actually have a much tighter integration between CPU and network because effectively in a system on a chip design, they are co-located. So the distinction between the network and the CPU is sort of going away because now the CPU actually has a much more direct control over the network resources. And so you can effectively see the two as being the same, two different sides of the same coin. So the research question that we're trying to address in this work is, given all this difference, if we were to redesign the network stack from scratch, how would we do it? How can we take advantage of all these new technologies in order to improve the performance? Clearly, a network stack comprises multiple different layers. So we have security, addressing, naming, and so on. Here in this work, we just address, or we try to address, two very simple questions. That is, how do we route packets? And second, how do we do the rate control? So let's start from setting out our goals. So the first goal is that we want to leverage path diversity. So since you have so many paths in our system, we think it's important that our network stack is actually able to take advantage of it. And also we would like to use them in a balanced way so that we don't have a hotspot in the network, or at least we minimize the chances of hotspot. Second, we don't make an assumption about the traffic metrics. So we assume that we want to support any workload, very dynamic, so think like cloud-like workload, where there could be new application coming up, they can have non-predictable traffic patterns. Second, we want to be able to achieve low queuing. This is sort of obvious. I mean, any transport protocol wants to achieve low queuing. But here it's even more important because now we have the fact that the fabric provides such a low latency that it would be a waste just to have a queuing delay in the network. And finally, we want to be able to support custom rate allocation. Like TCP try to achieve a maximum fairness. You can tweak TCP to achieve different kind of fairness, but it's very tricky. So we would like to have something that is very flexible and it's very easy to just plug in a different rate allocation policy. So let's start from the first step, routing. So we want to decide how we move a packet from A, the source, to B, the destination. So we look at different alternatives, and eventually we settle on what is called the valiant load balancing. This is a very old protocol. It was proposed more than 30 years ago. And there's a very simple mechanism. So the idea is that when you want to go from A to B, what you do is that you randomly select an intermediate destination. In this case, is the green node here, just showing up. And then what you do is that you route the packets through this intermediate destination. Now, when you have the next packet, you will select another intermediate destination, for instance, in this case, and then you will send the second packet of the flow first to this intermediate destination and then to the final destination. Now, intermediate destinations are not restricted to be on the shortest path. So, for instance, we can also select an intermediate destination that is up there. And in this case, we will route the packets through a longer path. Now, why does it work? So what is great about variant load balancing is that, as you can see, it's trying to take any traffic matrix and convert into a uniform one. So this means that effectively we can take advantage of all possible paths in the network and achieving a very good load balancing, while at the same time being independent of a specific traffic matrix. And that actually can be proved that the worst case performance actually is bound. Now, what is the price that you have to pay? Clearly, there is no free lunch. So what's the price? First of all, you have an increased path length that also turns out to result into increased link utilization. Now, there are some solutions to sort of balance this aspect. Mostly, you can use a locality-aware variant of variant load balancing, where effectively you weight the probability on which you choose a destination, an intermediate destination on the shortest rather than on the longer path. Second price that you have to pay is that since you're using multiple paths with different length, you're going to have out-of-order packet arrival at the final node. So in this case, again, what you can do is that since we are targeting a rack scale, so the diameter will be bounded, plus if our transport protocol can achieve low queuing, then effectively the JIT that we are observing at destination will not be massive. However, so far, what I discussed is sort of well-known. I mean, it's kind of textbook variant load balancing. We're not really doing anything special. But the key observation, and the reason why actually we think that variant load balancing is a nice choice in this context, is that since we're having distributed switching fabric, And since variant load balancing tries effectively to distribute the traffic uniformly in the fabric, what we have is that naturally, without any additional control overhead, any node in the system at some point will be aware of all flows in the network. So in this example, node C, simply by forwarding the packets from A to B, will know that there is a flow going on between A and B. And effectively, all the nodes that are on the packet path, they know that there is actually a flow between A and B. And eventually, after a few iterations, all nodes in the network will have this information. So this means that now every node can actually locally reconstruct the traffic matrix. It will be approximated, of course, because there are some dynamics, but it's going to be like a good approximation, at least in some condition. So now, if we move to the rate allocation problem, we see that we can really take advantage of this by effectively using the following, making the following observation. So since I know the topology, I know the routing protocol, and I know the traffic matrix, every node locally can derive what is the correct rate that should be assigned to its flows in order not to congest the network, and assuming some fairness property. So for instance, in this case, node A, node that is the only one in the network, so we'll just set the rate of its flows, assuming that it is the only one. Then at some point, node C, for instance, wants to start sending a flow to node D, in this example. So it will know about that there is a flow between A and B, simply because, as observed the packet before. Now it knows, of course, that there is also a flow between C and D. And so what it does is that it will set the rates accordingly. It will start routing packets using variant load balancing. And then at some point, the packet will also go through A. So now A knows that there is also a flow between C and D. And what it will do is that it will reduce its rate in order to match the new condition. So what is the key advantage here? And this is really I think the key point of this approach is that we have now what is considered to be was typically considered a distributed problem. That is how sources independent can actually agree on a common, or not on a common, like on a correct rate for each flow, such that you don't have congestion in the network and you don't have unfairness. Now actually has become a local problem, because now every node locally has enough information to derive this information. So two main benefits. First one, low queuing, because unlike TCP that has to always try to probe the network and try to reach the limit until when you start losing packets, or in a way some queuing are building up in order to detect that there is congestion, so you need to back off. Here we can, as soon as you start, you can immediately set the correct rate. And second advantage is that now if you don't want to have maximum fairness, but you want to have deadline-based, or you want to have tenant-based, or whatever is your rate allocation policy that you want to adopt, you can just replace the function. So it's just a function update. Now, I guess there are probably a few things that you're worried about. I just try to address a couple, and then we can discuss about the others. So the first one, probably you're thinking, said, okay, the example is nice, but in practice, it will take some time before the traffic metrics at each host actually become consistent. Like in this example, when C starts, A still doesn't know about C, so there is effectively a fraction of time in which the two rates are sort of disaligned. That's true. However, what we notice is that in many cases, it's enough just to reserve a bit of spare capacity. So when you compute your rate, instead of computing such as to saturate the line rate, you reserve something in the order like 3-5%, and this actually should serve as a slack to sort of absorb the newly created flows. Second thing that you can do is that you can also use short packets, so that order of 100 bytes, so that effectively you can speed up the dissemination rate. So when you start the flow, you start with short, small packets, and then what you can also do is that you can also use deterministic routing so that you maximize the coverage of the area, so that you reduce the convergence time. Second thing is that you can say, well, but computing the maximum fairness is going to be very expensive on each node, because effectively this, is potentially a multi-iteration process where you actually have to first find the first bottleneck link, then the second one, and so on. This is true in general, but in this context, what we see is that by using VLB, effectively what happens is that since the flows are distributed uniformly, effectively the bottleneck link is going to be the bottleneck link for most links. Like in our experiment, it was like for 90%, sorry, for most flows. So in our example, the bottleneck link was the bottleneck for 95% of the flows. So this means that effectively with very few iterations, typically in the order of 2 or 3, you are already enough information to establish the flow, the rate for all flows. Plus, you can also do some approximation. So in fact, I'll show you an example later on in the experiment where you can trade off a bit of utilization in order to achieve a faster speed. Okay, so much of this work is still very much in progress, and there are several aspects that we haven't really nailed down yet. And also, as part of this, we're also trying to build an emulation platform so that we can test this for real. So at the moment, I'm going to just present some simulation results. I don't want to draw any strong conclusion, but it's more just to give you a feel of what could be the benefits that we can achieve. So we just built a very simple setup in which we try to emulate the C micro platform, the one that I was describing before. So it's a 3D torus with 512 nodes. And then we have a very simple workload where effectively is a permutation matrix. We compare our approach, Rockscale, with 3 baselines. The first one is TCP. So this is what you would get today if you buy one of these C micro on the market. And by default, with TCP, we have the constraint that if you use vanilla TCP, we have only one path per flow. And we enforce this constraint in our simulation. And then we sort of created 2 idealized versions of routing protocol in which we assume that we have unlimited per flow queues. So this is clearly unfeasible in practice, but the idea was to sort of get an understanding of what are the upper bound of the performance. And in the first case, we have what we call ideal shortest path. That means that we use shortest path routing only by effectively spreading the packets across all possible paths, but constraining to shortest path. And second, instead, is we do the same, but this time we also consider non-minimal path as well. So this is the first graph. On the x-axis, we have the network load. So this means that if we move from left to right, we have the number of sources increased. And on the y-axis, we have the flow completion time, and the lower, the better. So this is the performance that we get with TCP, and this is the performance that we get with shortest path. And the difference between the two is due to the fact that TCP is constrained to use a single path per flow. While instead in shortest path, we can effectively use many more paths, so we have more opportunities for increase the throughput. This is a performance that we get with VLB, and as you can see, we can improve the performance a bit. And again, this is due to the fact that now we have even more paths that we can use because now we are removing the constraint of using shortest path only. And finally, this is a performance that we get with Rockscale. That is our protocol. And as you can see, we can very closely approximate the performance of VLB. Now notice that the VLB performance is actually idealized because they're using per flow queues, unlimited per flow queues in the network, while in our case we just use a standard drop tail queue. Now you can argue, well, you're just showing us the behavior at the tail, so what happened for the full CDF? So what we did is that we just zoom into one of the load point, and again, this is on the x-axis we have the flow completion time, so the lower the better. This is the performance that we get with TCP, so very long tail, not surprisingly, because again, it's due to the fact that we have single paths, so we are going to bump into some hotspots that are going to increase the tail. Shortest path, as you can see, now the tail is actually much shorter, but there is still a bit gap between the median and the tail. And again, because in some cases, just by using shortest path, you cannot fully utilize the bandwidth. Now, when we run VLB, instead, we have a very nice and narrow distribution. And again, this is a property of VLB because it tries to spread the traffic load. So we lose a bit on the median, but we gain a lot on the tail. And in general, for data center workload, the performance of the tail is actually more important than the performance of the median. And now, this is the performance that we get with our approach. Now, you can see that there is a bit of gap between the two. So we don't really approximate VLB all the way from the beginning to the end. And this gap is actually due to the approximation that I was mentioning before that we make in order to have the computation run faster. Okay, so I just want to conclude because I'm running out of time by saying that what I present today is really just scratching the surface. But we believe that there are many more interesting challenges and opportunities in this space. And I just want to mention 3. It's not going to be like an exhaustive list. I'm sure there are many more. But just to give you a feel of the kind of challenges that we can have in this new context. So the first one is that if we're now with technology like silicon photonics, sort of removing the distinction between local and remote resources, now what we're going to have is that a converged fabric. So we use a single fabric on which we multiplex storage, network, and memory traffic. So an interesting question is, do we still need to have all this variety of different communication protocols, like PCI, DDR, Ethernet, or we can actually converge on a single protocol? And in this case, what could be the model? Are we going for best effort, reliable? What about the QoS? Is going to be packet switched, circuit switched? Also, how do we share the bandwidth between different traffic? If we have memory traffic competing with network traffic, how the two are going to interact together? Second problem is that so far we only focused on what happened within a rack, but then at some point we also need to connect multiple of these rack scale computers together. And the idea is, how are we going to do that without introducing too much oversubscription? And finally, and this is in a sense is hinting at the bigger picture of the impact on the system, is that how do we provide this model to the programmer? Are we going to provide the illusion of a single shared memory space, or are we still maintaining the difference? Since now we have independent failure domain, what happens if, for instance, if you have your VM that spans multiple servers, but then one of these servers fails, so suddenly some banks of memory disappear? And scheduling. So how are we going to cope with the local scheduling on each server with the global scheduling across servers, since now the two actually are sort of converging? Okay, so super late, just want to wrap up very quickly. So we start by observing that there has been a lot of changes in data center technology. Some of these are still happening, and it's unclear which technology will win in the sense, but we think it's a good time for us as a system designer to actually step back and rethink some of the early assumptions. We just start looking at the network, and we think there are some interesting challenges because the network is changing. And we have seen that at the same time, there are also some interesting opportunities because there are things that now we can do, for instance, changing the routing protocol, sniffing the packets that pass through that we cannot do in ideal network. And finally, as I said, I think there are many more opportunities. Here in Cambridge, we have just started addressing some of them, but I really hope that as a community, we can actually put more effort into this area. I'm done. Sorry for the delay.
So there seems to be, this is very interesting work. There seems to be a tension between how randomly you spread the paths, and the penalty there is, of course, the stretch, versus how quickly other nodes learn about traffic. Have you thought about that at all?
Yes, it's a very good question. So the short answer is that we are thinking about, we are considering different alternatives. One solution that seems promising is that you can actually do the full spreading when you start the new flow because you want to maximize, and then actually once you start the new flow, then effectively you can now go to a more locality-aware solution.
I see. Makes sense.
That could be something that you can do. Also, for the first path, you can actually use deterministic routing. So instead of choosing randomly, you choose effectively the path in a way that maximizes the coverage. So that basically, you maximize the probability for a single path, for a single packet to actually cover as many nodes as possible. So that effectively, with few packets, you can actually cover the entire space.
So you have it.
Yeah, but without going crazy, of course, because
Okay.
If your flow is just one packet, you don't want to increase the latency too much. So we are sort of trying to understand what is the sweet spot between not increasing the latency too much with short flows, but at the same time also maximize the coverage.
Thank you.
And the good thing is that the latency is apparently is gonna be in the order of tens of nanoseconds, perhaps hundreds of nanoseconds. So you're not gonna pay too much even if you choose a longer path at the beginning. That's it.
Yeah, as a matter of fact, just to follow up with a comment for that, certainly our experience when we worked on those, it really radically blows your mind. The latency is so small that it really does make other solutions much more viable.
Yeah, exactly. So this is something that we want to take advantage of.
Hi, Dan Schatzberg from Boston University. These networks are really good at doing multicast flows as well. I couldn't think how you can still do this local operation and try to manage multicast flows and reduce jitter. Have you thought about that?
No. So in the previous work that was looking at different aspects, we have been looking at how we can take advantage of the multicast or also aggregation tree. So we have a version that effectively was improving MapReduce performance by building up an aggregation tree. In this context, we are at the moment only focusing on unicast, but you're fully right that multicast seems to be like a natural primitive here. And in that case, yes, we should think about how to merge the two together. So far, we haven't really given too much thought yet, but it's a valid point.
Thank you.